All right, hey guys, grade 11, IBDP chemistry, the higher level. So Gigi and Sophia, you can ignore this lesson one more time and go back to picking internal assessment topics for your paper, for your topic 1, topic 2, topic 3, okay? So we work on that, or you start the reading assignment I gave you for topic 4 on bonding, right? That's already assigned to you on the cognitive website. The rest of you in HL, you can get back to that reading over the weekend. But we're going to get through one more thing here with the section topic 13.2, color complexes in this chapter, okay? So I'm going to share my screen now to, okay, hopefully you can see everything here. So I will start off with what I want to practice. Yesterday, we were doing this PowerPoint. So I reviewed with you the basic rules and factors that causes color complexes to have like different colors, okay? Right, so let's do some examples, okay? Then I'll give you a worksheet that you already got in this email where you can do test-like questions on color complexes. All right, so in this question here, if you can see, they ask you which complex would have one highest energy gap, meaning the biggest split between your d orbitals. Remember, there are 5 boxes or 5 d orbitals. I'm in a coffee shop, so it could be a little noisy. Huh? So you're splitting 5d orbital, okay? And then part 2, absorb the highest energy light. Part 3, absorb the highest frequency light. Part 4, absorb the lowest wavelength light. Okay? So with that, do you notice that it's a trick question? That these are all the same thing. So basically, 1, 2, 3, and 4 are asking the same thing. Highest energy gap, but part 2, 3, and 4 is also about highest energy. So if you can remember, like that when you look at a wave, and so if I'm looking at this wave here, remember this is very high frequency, short wavelengths. The high frequency means high energy. And then of course, with the longer, wider wavelengths, it is slower, it is less energy and low frequency, okay? So then we know that in this question that I just showed you here, it is really the same thing, okay? It's the same thing. So really we're just asking between each pair of complex ions, like who's basically higher energy or will split the d orbitals more or absorb higher energy light or color. So starting with the first one, I'm looking at a complex of chromium and cyanide, and both of them have the same ligands, yeah? The complex ions charges are different for oxidation, but the same transition metal, chromium, chromium. So for this one, I would need to understand that each cyanide, in case you don't remember, maybe you haven't seen this document before, in my list of common polyatomic ions, Cn minus cyanide has a charge of -1 as a group, okay? So coming back to this one, if these are all Cn minus, 6 times that is 6 minus. That means to get an overall charge of 3 minus, this chromium will have to be 3, right? Because 3 minus 6 minus is 3 minus. On this complex, I have an overall charge for the complex ion as 4 minus. That means that this has to be a 2 because 2 minus 6 is -4 or 4 minus. So like we said earlier in the PowerPoint, that between these two, we will compare them by the oxidation state, and the higher the oxidation state, the higher the energy that it will absorb. So then it will split the d orbitals more. That means that the chromium 3 is the winner in this particular complex, okay? So I will choose this chromium 3 as my answer, right? The next one, I'm looking down here at the titanium and vanadium, okay? So I'm looking between these two. They have the same Lagrange water, same amount of Lagrange as well. Now they might have a different overall oxidation state, obviously, because they're different like transition metals. So here, the best way to answer the question is to compare the different transition metals. You're going to compare titanium to vanadium. So looking at Ti versus V, you have to go back to your periodic table. So in your periodic table, if you see here, this is Ti versus V. So if you can see the protons, okay, or should we say the number of electrons total is greater in vanadium than it is in titanium, right? So 23 versus 22. So vanadium has more protons, more overall electrons. So that means that between the two of them, when we talk about isoelectronic series, okay, of the same or similar transition metals, the one that has more protons and more overall electrons is going to have more interaction with your ligands, especially when they have more electrons, remember? So there's going to be more interaction between that vanadium with its ligands more than titanium. So in that case, your answer is going to be vanadium here, okay? To be able to compare these two. So this vanadium will absorb a higher energy light or color and split your d orbitals more. Make sense? And last but not least, the last two, both made out of manganese. Okay, so same transition metal. The oxidation state in both of them is 2 plus. The only thing that is different is that you have ammonia and water as the ligands. Okay, so but you got to look at your spectrochemical series here. Okay, this is the order, right? The highest energy ones are at the far right. So everything here is pretty much the same except for the ligands that are attached to your metal, okay? So you will pick the one that has the higher energy, which is in this case NH3. Ammonia has higher energy than the water. So this is the one that will be able to split your d orbitals more or absorb a higher energy, color, and light, okay? So that is how you answer this particular kind of question. All right, here's a slightly more tricky one, but still using the same concept you learned before. Let's say the problem is asking you this. A solution of a iron cyanide complex is red. So this is what I see and observe is red color. Part A, deduce the color of the light that is being absorbed by the solution. Okay. So part B, state the oxidation state of iron in this complex. So we want to get the oxidation state of Fe. That shouldn't be hard. And then part C is a little trickier. You're gonna treat the solution with some other ligand, something besides cyanide. And then that's gonna cause the color of the complex to change from red color to yellow. You need to explain to me what the heck is happening to cause these energy changes and state what is the possible identity, sorry, I spelled that wrong, identity of this mystery ligand. Okay, so let's start with part A first. Deduce the color of the light that is being absorbed by the solution. So I need to go back and look at my color wheel. So they said that I have a red. So if I have a red color, I'm looking here, that means the complementary color is green. So if I see red, that means green is absorbed. So you will answer green for part A. Part B, the oxidation state of iron or Fe in this complex. Okay, so we now know that cyanide is -1. 6 times that is -6. This is the overall charge of 3 minus. So this Fe would have to be Fe3 plus because 3 minus 6 will give you -3, okay? So that's the answer to part B is Fe is gonna be 3 plus for oxidation state. Then part C, treatment of the solution with some mystery ligand. So let's pay attention to this statement. If I use some other ligand besides CN, it would change the color that I see from red to yellow. So now we're going to talk about yellow. Go back to the color wheel. If I'm going to see yellow, that means now I'm absorbing violet, okay, instead of green. So used to be red and I absorb green. Now I see yellow and I'm absorbing violet. Okay, so in that case, then what are we supposed to talk about is what is happening with this. If I go back to my color wheel, when I had green absorbed, that was like around 500 nanometers wavelengths, which means that now when I have a new color, yellow, the violet is now absorbed. So this now goes from green to violet. So it went from 500 whatever nanometers to like only 400 nanometers for wavelengths. So my wavelengths decreased. I went from higher wavelengths to smaller wavelengths. So then, but then because it's lower wavelengths, I have to have a higher frequency or higher energy, okay? So with the lower wavelength, I have a higher energy color here. So violet, okay? The violet is going to be a higher energy than green light. So that implies that I'm splitting the d orbitals more, okay? So I'm absorbing a higher energy to split the d orbitals, the 5 orbitals. So I split those first 3 orbitals from the last 2 even more, just like we saw in this situation, like this, right? I'm splitting these two even greater than if I was using the other Lagan, okay? So with cyanide, it was probably like here. And then with this mystery one, I'm going up even higher. But from this spectrochemical series, I'm also asking you what is the identity of the mystery Lagan. The only thing that's higher than cyanide on this list is carbon monoxide, CO. That's the only one that could possibly fit this description of a mystery Lagan. And there's an entire university journal, by the way, about some students doing some crazy experiments to compare how the CO, carbon monoxide, splits the d orbitals much greater than the cyanide. But sometimes the data show that they were very similar in some situations, but whatever. That's beyond your scope in IB chemistry. So anyway, CO is higher than Cn minus. So that means you can answer that question with carbon monoxide being the mystery Lagan. And then the way you write about it is you would describe it by saying that the violet light is going to be higher energy than the green light, okay? And then that way it splits the d orbital more, okay? Like we see in the color wheel here. So again, part A absorbs green light if you see red. Part B, you know that your iron has a oxidation state of 3 plus. And then this last one is about violet light versus green. And then your mystery Lagan will probably be carbon monoxide, CO. Okay, so now that is done with this presentation. You are able to do, okay, this practice test question, okay, of the color complexes in section 13.2. So the first few questions are like paper 2 stuff. Okay, your answer is really, you can really just get very general definitions that you get from your notes, your textbook. Okay, so try them out, answer them. None of your answers here would be super long, even though I gave you a lot of space. Okay, and then once you get past all that, okay, you get to the multiple choice. Okay, so be very careful. Some of these are very tricky. They ask you to really think deeply and go in a lot deeper. So use your book and your notes to your best ability to really make sure you investigate every single one of your choices, okay? And sometimes the wording on these multiple choice are very close to each other. That the only difference by a little bit in just the word choice, so be very careful. So please go ahead and use this PowerPoint. I will re-upload this PowerPoint onto the okay, the Google Classroom, so you can use it again with the additional examples I gave you. And then that will allow you to be able to use that to do this practice test, okay? So I hope that is more than enough for you to have something to do for the whole period. So I am recording this video for you to watch. But yeah, because there's some internet issues here with the hotel that I'm at, right? So, and with that, I will just stop this lesson and hope that this will be useful to you. See you guys.